take it away.
Thanks. So I'm going to present my work mapping the larger scale strain rate over the Tibetan northeast Tibetan Plateau using Sentinel-1 INSAR data. So this is a work done in collaboration with authors from the universities of Oxford, Lorraine, Leeds, and Potsdam. And this paper is just came out in JGR. So this work is motivated by two reasons. The first is seismic hazard, because the northeast Tibetan Plateau is a very seismically active region with numerous magnitude greater than 7 earthquakes registered over the past century and many more in history. So creating a strain rate map in high resolution will help us improve our knowledge about where the strain is being accumulated, and that should be where the hazards lie, and also hopefully we can better quantify how frequently we should expect such hazard to come. And the second motivation is to better understand the tectonics. So in the northeast Tibetan Plateau, the tectonics is dominated by three major strike slip faults, which are the Altan-Tak and Haiyuan fault and East Kunlun faults. But there are also a lot more thrusts in the Tilanshan and the conjugate strike slip faults in the other direction. So previously, the geological slip rates have been dotted around only mostly the major strike slip faults, and very rarely were they measured in the other faults, the secondary faults. The GPS stations were installed at locations that are limited by the accessibility of the terrain. And in this area, which is already quite densely distributed, the GPS stations are spaced at about every 30 kilometers, which is still too long a distance if we want to quantify and visualize short scale velocity changes, such as across a creeping section. So hopefully with the high resolution INSAR data that we have available with the launch of the Sentinel-1 data, we can map the velocity and the strain rate across this area with much better, higher resolution. So in this study, we processed 10 ascending and 13 descending frames of Sentinel-1 data acquired between the end of 2014 and the end of 2019. So in total, this covers an area of about 660,000 kilometers squares. For each of the frames, we generate interferograms between each epoch and 5 consecutive links, plus 3-month, 6-month, and 9-month interferograms. So these data sets together give about 300 to 550 interferograms per frame, and spanning 4 to 5 years across 73 to 104 epochs. We processed interferograms at about, at about 100 meter resolution, and this data set gives us a theoretical uncertainty of the velocity millimeter per year. Due to the decent coherence in most area of the study area, the Northeast Tibetan Plateau, we have on average 86% of pixels unwrapped successfully. So in terms of data processing, we first generate the unwrapped interferograms using LIXAR and take from the unwrapped interferograms a atmospheric delay produced by the Gaco's weather model, and take out a planar ramp that is inverted from the network so as to get a flattened interferogram. The flattened interferograms will help us with identifying unwrapping mistakes using the NS-bus method. So we remove interferograms with unwrapping mistakes, refine the network such that we are sure the network is of good quality. And we invert a time series from the network of interferograms and fit a straight line velocity through the time series to get an average velocity across the 5 years with the associated uncertainties. The velocities derived in this method are flat because each interferogram has been flattened before. And as a result, They are all individually referenced and offset and potentially tilted from each other, as we can see in this track, which is here. In order to stitch them together and to put the INSAR line of sight into the reference frame of the GNSS, or a known reference frame, which can be provided by the GNSS, we invert for a planar ramp per frame, which simultaneously reduce the differences between the INSAR line of sight and the GNSS line of sight, as well as the differences between the INSAR line of sight and the frame overlaps. So as a result, so these are the inverted ramps, and these are the residues, which are Gaussian distributed and zero-centered, which is good. After applying the inverted ramps, this is what we have, which are the line of sight ascending INSAR velocities and descending line of sight velocities, now in the reference frame provided by the GNSS, and this is fixed Eurasia reference frame. On average, we can calculate the differences between the INSAR and the GNSS line of sight velocities, and the differences have a standard deviation of 0.87. No, the INSAR overlaps have a standard deviations of 0.87 millimeter per year, and the differences between INSAR and the GNSS have a standard deviation of 1.27 millimeter per year. So that gives us an idea of the quality of our velocity map. Now, if we want to decompose the line of sight into Cartesian velocities, we first used a method developed by Ling Shen at Leeds, where we first decompose the ascending and the descending velocities into an east and a subvertical velocity component. And this is the combined velocity from the vertical and the north component. Then we interpolate the GNSS north velocities and use that to extract the vertical component out of the subvertical component. If we compare the INSAR and the 201 GNSS east velocities and 124 GNSS vertical velocities, we get a standard deviation of the misfit of 1.14 for BE and 1.38 millimeter per year for BU. And in particular, we get a very good correlation between the INSAR and the GNSS in the east component, which is great. In order then to derive a strain rate map, we first tried a block median method, where all pixels in a 15 arc minute block of the INSAR BE map is reduced to a median value. We take the horizontal velocity gradients of the block median VE and interpolated GNSS VN, and combine the four horizontal velocity gradient components to obtain the second invariant horizontal strain rate. From here, we can clearly see this localized strain rate across the strike slip Haiyuan fault and across the East Kunlun fault. There are also focused concentration of strain rate at the fault junctions, which is pretty nice. And there are some strain away from the main structures. We can further interpret the strain rate field by comparing the strain rate with the velocity profiles. For example, on the profile 2 here across the East Kunlun fault, there is a strain rate peak on the fault, and that corresponds to the velocity gradient in the arctangent shape of the velocity profile, as predicted by the Okada dislocation model. However, across profile 1, we have almost linear velocity profile, and that gives rise to a much more diffused strain rate profile. Similarly, on profile 2, across the Haiyuan fault here, we see well-localized strain on the fault, and that corresponds to an arctangent shape velocity profile. However, across profile 1, on the velocity profile, we see a sharp velocity step, which corresponds to a creeping section on the Haiyan fault. And there is a secondary smaller velocity step across the Gulang fault. These two features are separate, but in the strain rate field, they are merged into this big blob of strain rate feature, which is not ideal. Ideally, we would like to separate them and to visualize this strain partitioning between different faults. So we need to increase the resolution or retain the VE map a little bit better. So instead of doing the block median, what we can instead do is to use a sliding median filter. So, and here I am using a median filter of a similar size, but sampling the median value at every 1 kilometer interval. That significantly improves the resolution of our filtered VE map. However, it also introduces a lot more noise in the velocity gradient map. In order to suppress the velocity noise in the velocity gradient, we can increase the filter window size, and then we can keep increasing, and we can see this noise keep going down. However, the next question is, how do we know when to stop? We can make sense of this increase in the filter window size and the effect of noise quenching by modeling a synthetic profile. So this is an arctangent dislocation model generated in red, hidden behind. And if I add Gaussian noise to the arctangent profile at 100 meter resolution, that's the same resolution as my INSAR VE data, and that gives me this noisy profile. After filtering and sampling the median value every 1 kilometer length, we can that will reduce my noisy profile into the blue dots, which hugs the red line a lot better. But still, there is some noise within the blue dots, right? And if I take a spatial derivative of the blue dots, that will give me this noisy blue bars, which are the velocity gradients across the profile. And this is with reference to the red profile, which is generated from the synthetic. So the pluses and minuses of the velocity gradients will always add up to something similar to the velocity step. However, the negative gradients, once they are squared and summed and square rooted to enter the strain rate fields, the negatives will cause overestimation of my strain rate fields. So that is the second invariant and maximum strain rates, which is not ideal because I want the total strain rate across my area to be conserved. So ideally, I would like to remove all the negative noise. And in this case, a 60 kilometer filter window is doing a good job. But is 60 kilometer really the best filter? We can do a Monte Carlo test and do the filtering across thousands of synthetic noisy profiles with a range of locking depth, a range of velocity steps, and with noise level of 0.5 and with noise level of 1, because I believe my velocities are have an uncertainty below this range or within this 0.5 to 1 millimeter per year range. And then these are the results with 30 kilometer filter, 60 kilometer filter, and a 90 kilometer filter windows. I am only plotting dots that represent synthetic profiles with a suite of locking depth and a velocity steps that after the filter, gives me a gradient, a velocity gradient profile, and with absolute gradient summed up to a value that is within 1% of the synthetic. So that is saying for a 60-kilometer filter, that is a suitable window for for any faults that has a locking depth between 3 to 20 and a velocity step between 3 to 15. And that is that applies to most of the faults in my area, given my knowledge of the geological slip rates, as well as the typical locking depth across continental crust. So let's go with 60. So on the left is the unfiltered velocity VE map, and on the right is the VE after median filtered with a circular filter window of 60 kilometer diameter. And using the same approach, I can calculate the velocity gradients from the median filtered VE and the interpolated GNSS north velocities. And this gives me a much better second invariant horizontal strain rate field. And we can see this is a lot sharper than what we had before. Also, if we increase the upper bound of the color map from 80 to 400, we can highlight the creeping sections from the background. If we draw a profile across it, we can see the extreme creeping sections are having this extreme strain rates exceeding 400 nanostrain per year. And we can also plot the dilatation rate and the maximum shear rate and compare these two maps. So for the maximum shear rate, we can see this strike slip motion along the Haiyuan fault dies out as we go into the Qilianshan, where the strike slip motion transitions into thrusting. And that's where we have strong contraction and dilatation. In addition, we can also see focused strain at fault junctions. And these are contractional signals because they are negative dilatation. And this is suggesting volumetric changes at the junctions. Here we are seeing an unexpected fingering of the strain rate. And let's see why we have that. So this strain feature is a result of the velocity step of the green and the yellow here, which is visible both in map view and in profile view. So this might suggest there is an extension of the Dabanshan fault here, which had an earthquake about 100 years ago. On the eastern termination of the Haiyuan fault, we can also see this contractional strain, which is also unexpected. If we zoom in, we see this feature stems from a southern branch of the Haiyuan fault, which was previously mapped, and that can be seen from the hillshade, which is quite convincing. Previous studies also suggest that there is an extension of this segment along the southwest flank of the Quwushan. However, we don't observe any strain rate features across this mapped fault. Instead, the shear strain bends southward and it transitions into contraction in the north-south direction. And this feature comes from the velocity gradient across the east velocity map. We can see the west-hand side is moving faster towards the east than the east-hand side. And similarly, in the vertical velocity map, we are also seeing the west-hand side moving upwards faster than the east-hand side. If we take a closer look at the hillshade, we can see inside the valley to the west-hand side and inside the valley across the Quwushan, but in the middle, there is a very smooth fan surface. This slope has a back tilt at the last 1 kilometer or so. And as a result, we are also having diverted drainage away from this feature. So whatever is going underneath, whether it is a fault or a fault, which was previously unrecognized, might be responsible for pushing the crust on the west faster towards the east and uplift the left-hand side, the west-hand side, faster than the east-hand side. And this feature, if present, which will warrant more field investigations, if present, that might help terminate the strike-slip motion on the Haiyan fault towards its east. Last but not least, we have these contractional strain observed across the Longyanxia Reservoir. And this is where we have this subsidence centered around the reservoir. And also from the east velocity profile, we can see the west-hand side moving faster and faster towards the east as we approach the reservoir from the west. And if we approach the reservoir from the east, we see it moves eastwards slower and slower as we move towards the reservoir. So this is suggesting a pinching from the subsidence of the gravitational loading of the reservoir water column. And as a result, this pinching effect is causing the contractional strain across this area. So chances are this is not a tectonic load, but a hydrological signal. Here, let me present a comparison between an INSAR strain rate and a GPS-derived strain rate. So this is our INSAR strain rate, and the second panel is a GPS strain rate published by Wang and Shen 2020. We can see the main features are similar, which are the Haiyuan and East Kunlun faults. But the wavelength of the features are a lot longer in the GPS-derived strain rate fields, because the GPS measurements are much more sparsely dotted around the area. So in order to do a quantitative comparison between the two, I filtered my each element of the strain rate tensor with a 150 kilometer mean filter and calculated the differences between my filtered strain rate tensor element and the corresponding element from the GPS-derived study. Then I calculated a second invariant of the differences of the tensor elements, and that gives me this map. And despite the noise in the corners that are associated with desert and here associated with forest, the misfits here average to 10.5 nanostrain per year, which is about the level of uncertainty that we would expect in our strain rate field. If we then compare these two strain rate fields in profile, we can see that indeed they agree in the long wavelengths, and but in the INSAR strain rate field, we get a better localization onto the fault structures, and we can see the strain distribution at much higher resolution. So INSAR-derived strain rate is giving us, telling us more interesting or releasing or partitioned between the different fault structures. And in addition, we can see secular crustal deformation caused by non-tectonic feature as well. I recognize my talk is fairly short at the moment. I have additional content prepared if people are interested in the next section will be the interpretation of the vertical velocity field. But at the moment, I can also take questions about the strain rate field part of the study if people are interested in asking, if there are any questions.
Actually, there is one question on that particular, someone's put a question in, so if you want to answer it now, we can. The question comes from, I'm so sorry for my pronunciation, Peter Kreisvik. Do your results shed any light on possible recent activity of thrust structures within the northwest Chidan Basin imaged by seismic data? A particular set of anticlines there.
That is very interesting. I would I would say, well, if there's any like anticline, then I would be more interested in probing the vertical velocities. And also, I actually don't know where these specific faults are. Yeah, I'm sorry about that. Oh, the Chidan Basin, northwest, the Chidan Basin. Oh,
that's my pronunciation, sorry.
that is, I think that is already out of my study area, But then, yeah, that will be a very interesting next challenge with INSAR, which is how do we know any vertical signals that we observe are actually tectonic in origin? Which actually leads us very naturally to the next section of what I've prepared here.
There's one other question that's come through. I'm not sure if it's related. Maybe you want to take it at the end.
Okay.
It's Athanasios Ganis has asked, are your strain rate results in favor of a fault-controlled model of continental deformation in northeast Tibet or large-scale crustal flow?
Okay. Yeah. So the previous there was another time that I also presented a similar material, and I titled my talk block model versus continuum, new evidence from INSAR. So I guess I would not say it for definite, but I'm very happy to present the result and for people to make their own interpretations.
Cool. Okay, maybe we can come back to them at the end of the talk as well then.
Yes. Cool. Okay, so all the results that I presented here, they are mostly derived from east-west velocities, right? And then together with the interpolated north velocities from the GNSS. So, yeah. So there's another vertical velocity field, which I haven't really touched upon. And so I can spend the rest of the talk trying to take people through what I think the vertical velocity is telling us. Well, the main striking feature of the vertical velocities is that it really doesn't look like the east velocities, and it's a lot of the features are much more shorter wavelengths than the east-west vertical velocities. So let's compare it with something that we are more familiar with. So first of all is the topography. So on the left, we are seeing highland on the southwest and the lowlands in the northeast. And in the vertical velocity map, we are seeing kind of the opposite with uplift most in the northeast and the subsidence across most of the highlands. So why is that? We'll probably get to that very quickly, but then another striking feature is that a lot of the uplifts and subsidences, they're of very short wavelength. And I think to most geophysicists, this will mean the feature causing this change is fairly shallow. So let's compare the vertical velocity with something that is shallow on the surface, and that is the land cover map. So and now we can already start to see some patterns of similar wavelengths and of similar shapes. We can calculate a one-to-one correlation between each of the classes and the corresponding pixel in the vertical velocity map. And that gives us this result. We see there are 3 classes which are systematically away from 0, which means there might be systematic subsidence on pixels that are represented by snow and ice, classified as snow and ice. There are uplift over pixels that are classified by as flooded vegetation. And there is a systematic uplift on pixels classified as water. We know INSAR decorrelate over water surfaces. So these water pixels classified as water, if they have vertical velocities, they tend to be on the edges of a lake or on the riverbanks, so within the INSAR resolution. So the common feature across these 3 classes are they are all associated with water. So let's first look at classes to do with ice and snow. So on the left, so I'm plotting the contour here, which is the contour extracted from the permafrost zonation map. And the higher the value, the more likely this area will have permafrost. So we can see most of the light blue pixels, which are the classes representing snow and ice, fall within this contour line of 0.5 permafrost zonation index. If we zoom into this corner, we can see the permafrost happen at high elevations. And this is also where the blue pixels lie, which are the snow and ice. So we are more convinced that the subsidence, which also happen across within this contour line, is very likely to do with the subsidence or the melting caused by the melting of the permafrost. And the drainage is flowing out of the peaks where the permafrost is melting, and it is draining into the lakes and draining into areas and maybe internally draining here or draining towards the north. Right. And where this river is draining, carrying water from the melted permafrost, is also where we see a lot of the uplift. And here, this is internal draining, and we are also seeing an area with focused uplift signals. And we notice there are some polygons in the north, away from the Tibetan Plateau. And these polygons agree in shape with pixels that are classified as farm. By farm, I mean crops in the land cover map. And we can see they match each other very nicely in shape. And if we zoom into an area that is highlighted with deep blue, which means it's subsiding very quickly, then we see this. So this is an area where oasis is being built into the desert. And here the land is irrigated by pumping groundwater. And this is where we are seeing subsidence signals. And this is why we see subsidence on pixels classified as crops. However, there are also other areas like this, which are showing uplift, but it is not classified as crops. Of course, it's not pumping groundwater, but why is it uplifting? So let's look at the land cover map again. So this polygon is dominated by pixels classified as background. So what's wrong with the background? Similarly, there's another patch here dominated by uplift, and that's also background. Let's take a closer look. So these here I am plotting VU pixels with value greater than 1.8 millimeter per year on top of the hillshade. So this is where we see the water drainage of the meltwater from the permafrost peaks in the Chilean is coming down, and it happens to be blocked by a linear shaped ridge, which is preventing the outflow of the water. So the water here is ponding and accumulating, which suggests the uplift signal is most likely due to this accumulation increase in water content in this area. And similarly, on the second polygon that we just had a look, this uplift signal is where three drainage systems join together, and this is an area of internal draining. So again, with increased flux of water, we see uplift signals. And it turns out this patch is here, and this triangle is here. It turns out there are other areas with also rapid uplifting signals. And if we plot the major drainage on top of it, we see they are at various places along the track of the Yellow River. So if we zoom in, we see, so first of all, this is the Zoic wetland, where the Yellow River coming from the multiple tributaries are bent around because it hits the topography here. And a lot of uplift signals here actually correspond to the flooded vegetation class that we had earlier. So these are the flooded vegetation in this wetland, and they correspond to the uplift signals. And as the Yellow River comes out of this bend, this is the Longyangsha Reservoir, which is subsiding and loading water. And as the Yellow River comes out of it and joins this Xunhua Basin, we see this uplift signal trapped in the basin. And this is where the river outlet is again blocked by a linear ridge. So it seems whenever a drainage hits a topographic barrier, we are seeing uplift signals. And this could be to do with soil moisture. And if we are interested in getting the real signal that is of tectonics origin from the vertical velocities, we would have to find a way to discriminate and to make sure the verticals and to correct for such effects, which might be due to drainage or soil moisture, and so as to be sure that any vertical velocities that we are seeing are from tectonics. So to summarize, in the vertical velocity map, we are seeing a lot of features that are to do with permafrost melting. So that's more like a climatic signal. And then reservoir and farming. So that is more anthropogenic signal. There is a signal to do with hitting the topography, and hopefully after correcting all of them, we'll have a chance of getting out any tectonic velocities in the vertical sense. So that's all for my talk. Thank you very much.
Brilliant. Thank you so much, G. That was great. I really enjoyed that. If you have any extra questions for G, please feel free to put them in the chat or the Q&A box. We'll get to either of them. We can maybe, if you want to discuss any more of those the previous questions, we can. I had a question which might actually be something I should already know. But with the GPS velocities, can you get vertical and compare them to what you're doing here with this vertical?
Yes. Yes. Okay. So after the decomposition of the line of sight into east and vertical velocities, I did make a comparison across these two profiles. So there is much better agreement within INSAR and GNSS in the east components. And in the vertical components, the vertical component is a component where the GNSS has poorer control. So the GNSS vertical are associated with larger uncertainties. And with my method of placing the INSAR line of sight into the GNSS line of sight, I use the uncertainties to weight individual stations. So it is reassuring to observe here the good quality vertical is also matching my INSAR vertical better than the GNS verticals with larger uncertainties. So yeah. Cool. So I guess it will be interesting to compare the time series of the GNSS and INSAR in the vertical and see if they can give us different clues.
Yeah, it seems like it seems like the vertical is going to take a lot of really, like, you can create these huge maps, right? But every single signal you have to then go and individually investigate. Do you see a way of making that easier in the future?
Yeah, this is hopefully what I'll try to do in my postdoc at Leeds, where I'm going to create a velocity and a strain rate field for the Tian Shan region. And that is filled with thrust faulting. So it will be a challenge to tackle, certainly. And so maybe the first thing that we can test would be whether this hydrologically related signal can be removed if we mostly measure, take interferograms that span the whole year, or if there's any seasonal signal in it, maybe we can remove them from the time series. But yeah, a lot of work still needs to be done and tested.
Cool. Well, I'm glad that you've got the postdoc to do some of that work and some of that testing.
Thanks.
I wonder if you want to elaborate on this question from earlier about the fault-controlled models or the continental deformation on large-scale crustal flow. Is there?
Yeah, I guess the higher velocity fields definitely provides constraint. So in terms of crustal flow, does it mean like channel flow, or is it just like a fluid like deformation?
I'm not sure.
Right. Yeah. Yeah. But like, let me see if I have any slides here. Yeah, so I guess with my strain rate map, we already know that there could be features that can be continuously added to the block models. So in existing block models, people are already putting in more and more in a smaller blocks. And so if we were to incorporate the INSAR-derived strain rate maps into block models, that might help refine the block models, or it could totally make it too many blocks in that. Or I guess another question would be like, quite often I don't see all four edges of a block in my strain rate map. So it's another question of, if it's a block, how do we close it? close each block and then make it like continuous in space. And also, yeah, or it could also be because I have poor resolution in the north velocities, such that the contribution to the strain rate map is unbalanced between the gradients of the east velocities and the north gradients of the north velocities at the moment. It is probably okay for an area dominated by east-west striking strike-slip faults, because we see most of the gradients across the east velocity field. But it also means we might be losing some strain that might be accumulated on faults like this. There are strike-slip faults and striking more or less north-south. And if we had better control of the north velocities, then maybe that will close my block. I don't know.
Yeah, cool. I think that that's quite a very valid point and a very interesting discussion point, that that certainly your faults don't necessarily define blocks or the edges of a block. I do wonder, I mean, this certainly highlights a handful of faults out of that fault map, right, rather than all of the faults. So I don't know, like maybe it can help condense the blocks into the most important ones.
Yeah. And also add maybe, like, if this is proven to be a real feature, then maybe add some features to a bigger block like this. So there might be another thing going on here. Or I know there are squidgy blocks introduced in block model as well. So potentially they are accounting for those secondary features that I might detect with INSAR.
Cool. Thank you so much. I think that that's a very cool discussion. There aren't any other current questions in the chat box. So please do get your questions in very quickly if you have any, because otherwise we will finish up early.
I had a quick question, Chi. So on your previous section, you mentioned the subsidence around the reservoir. Do you know the creation date of that reservoir?
The reservoir, I believe, is created, I don't know exactly the creation date, but then I did find out a paper, well, I probably didn't put it here. So yeah, so another paper that extracted the reservoir water level over almost the same period as my observation. And there is a systematic increase in the water level through this period, which is probably the cause of this subsidence that I'm observing. Yeah, I don't know whether what happened before that date, before Sentinel-1 was launched, whether there was systematic increase or not.
We have a comment and then another question. So Athanasius has said you can start defining blocks by looking at large areas characterized by minimal strain rates, e.g. less than 10 to 20 nano somethings per year. I'm actually not sure what NS stands for.
Nanostrain per year.
Nanostrain, thank you. And Peter has asked, there are thin-skinned structures detached within the Eocene evaporites, the entire Tibetan Basin. Again, with my pronunciation, apologies. Some are thick-skinned rooted within the deep basement. Can your model distinguish them somehow?
I guess that would require further modeling based on this velocity field, right? I'm not sure whether the strain rate field itself can differentiate that for sure. I don't have experience with that. And I think if it's in the Tibetan Basin, again, it's in further west of my area. So I don't have the data covered for that to know the difference. But I guess fault model, like any 2D profile modeling based on the east and vertical or line of sight velocities might give a clue.
Yeah, I think that also one of the PhD students in our research group is working in a different part of Central Asia, and I believe that she's doing some strain rate map work, and there are evaporites there, and I think that she's working on some of the faults and thinking about if the evaporites are increasing the strain rate. This is Roberta Wilkinson's work. So I think that she's seeing higher rates around the evaporites maybe, but I don't want to speak for her work. But certainly it requires like a bunch of extra modeling in order to understand what's going on. Yeah. And yeah. Cool. Well, there are no other questions, so maybe we'll call it 4 minutes early. Oh, and Athanasius is saying evaporites are good for creep and increasing the strain rate. So yes, exactly. But yeah, no, it's not, the maps aren't picking up the evaporites directly, right? You have to know that they're there and then model the faults, as far as I'm aware.
Mm-hmm. And I guess if it's like in terms of increasing creep rate or strain rates, that's more like making the peak narrower and higher. So maybe the overall tectonic, like if you measure it with the GNSS, the longer wavelength strain wave might still be what the tectonic background forcing is making it possible. It's just if it's creeping, then it's a shallower feature, it's sharper and like a shorter wavelength. But then if we integrate across the profile, a very narrow and a tall peak might integrate to a similar value to a broader and smoother peak that might represent a locked section.
Yeah. Cool. Well, thank you. I think we can probably call it there. Thank you everybody for coming along and asking such cool questions and also participating in the conversations. And thank you so much, Chi. This was a wonderful talk, and it's so nice to see all of your work come together. These are spectacular maps. There's a wealth of knowledge here. So thank you, everybody, and we will see you again in August. Again, we're taking a break for July, but we'll see you in August, and keep an eye on your inboxes and on our Twitter feeds for upcoming webinars. And I'm very excited to be handing over to Scott and Chi to be organising the webinars from here on in. Thank you both.
Thank you, Tamara, for your work.
And thank you, Scott, for staying along.
Yeah, thanks, Scott, for joining me in co-organising and then staying on. Cool. Well, thank you, everybody, and we will see you next time. Thanks, Chi.
Thank you. Bye.
Thank you. Cheers.
Bye.